This paper is Federated Calibration and Evaluation of Binary Classifiers, and it's joint work with Igor Markov at Meta. So this work is based within the federated computation model. That's a relatively recently emerged model that captures privacy-preserving computations over a distributed collection of users at potentially very large scale. In terms of computational models, in some ways it resembles the MapReduce model, but with additional emphasis on privacy preservation. The basic idea is that as much as possible data stays on client devices and only small numbers of sufficient statistics are shared. This captures the notions of data minimization and purpose limitation. In addition to this, we may enforce various forms of differential privacy and secure multi-party computation to protect the data while it's in transit. Within the area of federated computation, there are different subfields such as federated learning, which is concerned with the training of distributed machine learning models, and federated analytics, which captures a broad class of statistics gathering. And collectively, this notion of federated computation builds on a selection of different primitives for various tasks, such as sums, counts, and other things wrapped up in privacy and security guarantees. What this talk is concerned with is thinking about the ways in which we can use federated analytics to support federated learning. Right, so most of the work in federated learning so far has been around that core training part of the machine learning procedure, basically around updating a provisional model based on information from the clients in the form of gradients performed over a large number of epochs until it converges to an accurate model. But if we look at the end-to-end performance of machine learning, there's many other steps in there in order to maintain and perform machine learning at scale. So before we perform the training step, we need to look at feature selection and feature normalization. After we've trained a model, we need to know, well, how well is it performing on current and future data? And then we need to maintain and monitor the performance of that model over time. Each of these concerns represents a separate piece of research that brings the same privacy concerns as the core aspect of federated learning training. In other words, we need to make sure that the privacy of the data held by individuals is protected to the same level. So within this work, in this paper, we look at a number of different characteristics and properties of a machine learning system that we might want to evaluate. In this talk, I'll emphasize area under the curve, a measure of quality of the classifier. We'll talk about it in a bit more. But also in the paper, we look at calibration curves, so being able to map the confidence scores of a classifier into a probability, and other metrics like precision, recall, accuracy, and so on. So we're looking at the binary case. What that means is that in the federated setting, each client has a collection of examples with a ground truth label, which is either positive or negative. And these statistics and measures are based on comparing the ground truth label to the label predicted by the classifier. So a core concept here is the notion of a score function. Right? A score function is a way that a classifier takes an example and maps that example to some score in the range 0 to 1. Right? So all the sort of the hard work in building a classifier goes into defining the score function based on training a model. And we will abstract that as a black box. And in this, we'll just assume that we're given a classifier, described by a score function. What we then want to do is understand how does this score function behave as we look at both positive and negative examples. So this picture in the top right shows, as we look at the scores from 0 to 1, how many times do we see those scores occurring? What's the density of that score for the positive examples? That gives us the positive score function, and for the negative examples. And what we like to see is that typically we see more positive examples given a score that's higher, that's close to 1, and more negative examples that's given a score that's lower, that's close to 1. Right. The essence of the ideas in this paper are to then represent these continuous score functions as discrete histograms. Right. So what we'll be concerned with is building histograms that represent the score function. So in the lower figure, what we see is, as a dotted line, that positive score function represented as piecewise constant function. So essentially a histogram that approximates the frequency of each different score range. And what we'll do is we'll look at how to build this histogram in different models of federated computing. So there are three different models we consider. We consider the secure aggregation model, where clients report information to a server, and the server gets to see only the sum of the inputs from all the clients. The local differential privacy model, where each client sends a message that achieves a local version of differential privacy, and the server gets to combine those together. And a distributed differential privacy model, where the clients each add small noise to produce an overall distributed privacy guarantee when those noised inputs are aggregated by the server. So the key thing for us is that we can compute score histograms under each of these different privacy models. And in the paper, we go into more detail and discuss how that's done, building on prior work that's looked at very similar questions previously. Essentially, the core idea across all of the three different models is quite similar. We can do this in two rounds, right? In the first round, we'll make use of approximate quantile functions within the relevant privacy model to learn the quantiles of the client score functions. So the 10 percentiles, 20 percentiles, and so on. And we'll use them to define bin boundaries for the final histogram. And in the second round, we'll go back out to clients with the bin boundaries that we've learned and learn sort of what the frequency distribution is within each of those bins, right? So in the picture below, in the first round, we've learned these set of quantiles of the score function. In this case, maybe let's say it's the positive score function at 0.05, 0.09, and so on. In the second round, we go out to clients and ask them to materialize their data within this score function. So in this case, we have a client, maybe that client's score value is 0.1, so they place a 1 there for their example, and this gets aggregated, so across all the clients, we end up building the full score function. Now that we have that score function in a histogram format, we're going to use it to find the values, the approximate values of various different histogram metrics. So we'll focus on area under the curve, right? So the area under the curve is standard concept in machine learning that says, given a score function, how good is that at representing the data? So what we're looking at is the curve that trades off false positives and true positives, right? So this curve says, as we vary a threshold t, what's our false positive rate and true positive rate for each choice of t? And then that curve has an area. We look at the area under that curve, and that gives us a measure, right? We're looking for as large an area under the curve as possible, close to 1. Right? An area under the curve of 0.5 is just equivalent to random guessing. So the way in which you might compute this metric, this area under the curve metric, in a non-private setting would be to gather lots of examples, look at the score of each example and the true label of each example, compute this score, compute this curve, and then work out what is the area under that curve. Right. That's problematic in the federated case, where we don't have all the examples together, we can't look at them all together. So what we'll do is we'll transform this into something where we can use the histogram. So the first step is to make an alternative interpretation of the area under the curve, where another interpretation of the area under the curve is the probability that a positive example is ranked more highly than a negative one. Right? So ideally, we'd like most of the positive examples to be ranked more highly than most of the negative examples. So that slightly simplifies the computation. It says that we need to now just compute the number of correctly ordered pairs divided by the number of all pairs. That's still difficult in the federated setting where we don't have pairs of examples together. They can be distributed over multiple clients. So what we can do instead is go back to that score histogram and look at the number of counts of examples in different buckets, right? So we'll look at the number of negative examples in a bin and the number of positive examples in a bin that's below that, multiply those two together, and that will get us information about how many disordered pairs there are. Right, so we can compute the sum of all of those disordered pairs. We'll have some uncertainty because we don't know the exact ordering of pairs of examples that fall in the same bin, and that will contribute to our approximation error. And in the full paper, we analyze that approximation error as a function of the number of examples, the number of bins, and additionally the privacy parameter for differential privacy. So I'll now show some empirical results that show how well this works in these three different models that we look at. We looked at a variety of different data sets, and I'll show results here from a Kaggle data set called Tabular Challenge. And what we look at is we look at the accuracy of our estimation of error under the curve against the exact value. First, based on a first approximation where we just use a uniform histogram, a second approximation where we use the quantile histogram that I talked about, and then also try and measure different estimates of the uncertainty. And we'll do this exercise in the three federated models we mentioned: secure aggregation, where there's no noise added, distributed differential privacy, where a small amount of noise is added to by each client, and local differential privacy, where each client adds enough noise to protect their own data. So what we see, unsurprisingly, is that the results are very accurate where no noise is added, and as a function of adding more buckets, the more buckets we add, the more accurate we get, and the accuracy improves as a function that's quadratic in the number of buckets. So doubling the number of buckets improves the accuracy by a factor of approximately 4. In the distributed differential privacy noise case and the local differential privacy noise case, there's a trade-off here. After a certain number of buckets in the histogram, we stop gaining accuracy because the error in the estimation is dominated by the privacy noise. Right. Again, our analysis in the paper predicts exactly this performance, and these empirical results help us to see that in the distributed case, a small histogram of about 20 buckets is sufficient to get an error that's close to 1 in 1,000. And for local differential privacy, we can get a slightly larger error in the limiting case with, in this case, privacy parameter epsilon equals 1. So in summary, we've looked at this data management question around how do we manage and deploy classifiers in the federated setting. And a key learning here is that this idea of histograms is a very powerful tool. Right? There's a lot of study of this from the privacy community and how to build a histogram. So if we can map the quantity we want to measure, the analysis we want to do in terms of histograms, then we can leverage those techniques for building histograms in a variety of different privacy and security models. And as a more forward-looking approach, we can conclude that federated computation has a lot of potential within machine learning and data management communities. Lots and lots of emphasis has gone so far on federated learning. And within federated learning, lots of emphasis has been on the core training step. And that to me says there's lots of questions for future work around, how do we understand the full pipeline of machine learning and deploying it in a real world system? How do we strengthen the ability of federated analytics to further understand behavior and properties within these federated distributed settings? So with that, I will conclude now, and thank you very much for your attention.